Hello, welcome back. What are we going to talk about today? Today I want to get into questions of scaling. How do we get the basics that I've introduced in the previous lectures up to the larger sorts of systems that we might want to build cognitive models out of? And in particular, the video that we're seeing here is using all the techniques that I introduced in the last two sessions, and somehow it's able to, you're presented a visual image of a 4, presented a visual image of a 3, show it a question mark, and then it mentally counts 4 plus 3 is 4, 5, 6, 7. Somehow that whole system needs to get converted into vectors, functions and vectors, and differential equations, which is an interesting challenge. And such a system is going to get pretty big because we're going to start using a lot of neurons. So I'm going to start by talking about this using lots of neurons aspect, and then get into how we start representing symbols. So again, the recap of the last two sessions. If we can take an algorithm and express it in terms of vectors, functions on vectors, and differential equations, and if those functions are reasonably smooth, then we can just use the techniques that I've just shown to just take any algorithm and map it into spiking neurons, or non-spiking neurons for that matter. Which is great. I mean, that covers a lot of things. And in theory, I mean, there we go. Now we can do everything, right? The systems that I've just described, that would be enough to build a Turing machine. Yes, you can therefore use the system I've just described to implement anything you want. But there's some practical limitations here. First of all, if we're trying to model human cognition, well, we have a hard limit of, well, how many neurons are in the human brain? And this is somewhere on the order of 100 billion, which seems like a big number, but definitely if you were going to attempt to just build a Turing machine out of what the components that I was just showing here, you would hit those limits pretty quickly. But more vitally than that, there's also, if our point here is to model things after the human brain, then we're also want to pay attention to the organizational structure of the human brain. All right. And so that puts sort of constraints on the algorithms that we can implement. And then even more importantly, is this timing aspect. That look, if I tried just implementing some arbitrary algorithm by just sort of taking traditional computer science algorithms and converting them to this very, very, very low level and just implementing Turing machine and implement whatever algorithms I wanted on top of that, we would hit this issue that Turing machines generally don't have, which is that, well, the timing matters. You know, if each individual step is being implemented by spiking neurons, we know how long each step takes. And so if we take an algorithm and go and implement it using the techniques that I've just shown there, and it takes 4 hours for someone to recognize a word, then that's probably wrong. All right. So yes, you could go implement any algorithm that you want, but if you want to actually try to claim that what you're implementing is something to do with human cognition, there's pretty huge constraints that are now on. And so but still, that ends up giving me, that's my task, that's my job, this is what I've been doing, is, well, let's take existing cognitive models and convert them into this form. I'm going to take existing algorithms. That's great because I don't have to come up with new ideas. That's wonderful. I just have to go and see what algorithms are out there and go and look at them and go, okay, well, I can't implement exactly that, but if I modify that algorithm slightly, then maybe I can turn it into functions and differential equations. And that's what I want to do, is I want to go and using that approach to try to model the human brain. But there is a little bit of a question there. Is this a feasible thing to do? I mean, I hope over the last two lectures I've convinced you that it's a possible thing to do, that we now have the techniques to do that, which is great and an improvement, because when I was during my PhD, I would have said that all the stuff that I described here, that this just wasn't a useful approach to research because there's no way you could do any of this stuff. but now that I know that it's possible to do all this stuff, cool. But it's possible. Is it feasible? What do I mean by is it feasible? That video I showed at the beginning of that brain model solving a really simple cognitive task of 4 + 3 = 7. So that was the SPAWN model that we published in 2012, the world's largest functional brain model. 1 second of that video took 2.5 hours to generate. On what was at the time, fairly fancy computer, and it was only 2.5 million neurons. Human brain has 100,000 million neurons, so that means if I was going to use exactly that same approach to run a model the size of the human brain, 1 second of simulation time would take 10 years to compute. This is a problem. And I think it's something that if you're interested in doing this sort of connecting behavior down to the neuroscience, you need to be aware of this problem and need to keep it in mind when deciding your research. Because it was great when we first put together that model. All right, the fact that we could just do it was a huge advancement. It was a big hassle because, yes, 1 second of simulation was 2.5 hours. So we just ran lots of computers overnight a lot. But we really want to improve that because that's making it much more complex to do research. Now, the nice thing is, even though we're doing a bunch of weird math in order to generate our models, when we're actually running our models, it's a fairly simple system. Like this, all it is neurons, spikes, connections between neurons, connection weights. All the weird math that I've been showing is just ways of generating those connection weights. And everything that I've been showing is sort of agnostic about what exactly your neuron model is. Most of the time we've been talking about leaky, integrate, and fire neurons, but in theory it could be whatever neuron model you feel like. But so, there's our standard differential equation for one neuron. That's the leaky, integrate, and fire neuron model. But it could be something else, but that's still a pretty simple equation. The spikes are pretty simple. When voltage reaches some level, you produce a spike output. That postsynaptic filter, the thing that turns a spike into that release of neurotransmitter and then decaying, that's really, really simple and efficient to implement. It's just a low-pass filter. It's 1 multiply. It's pretty straightforward. And we get a really cool advantage that traditional neural networks don't have, and that is those big giant connection weights that we're computing. So, if I have 100 neurons connected to another 100 neurons, normally that would be a connection weight matrix of 100 by 100. That's 10,000 connection weights. The way that we compute using the NEF, we generate those connection weights, is by taking your decoder matrix and your encoder matrix and multiplying them together, and that gives you your weight matrix. But if you want to do things a little bit more efficiently, instead of multiplying them together to generate that weight matrix, you can just keep the components around, which is much less memory. So instead of say a 10,000 connection weight matrix, you now have say a 100 by 2 and a 2 by 100 matrix. So that can make the implementation much more efficient. But that's it. That's all that we need. And so maybe we can find better ways of implementing and more efficient ways of implementing this. So the very first thing, of course, that we did, because when we ran that first model, that first SPAWN model, that was just running on the CPUs. So the very first thing we did was, all right, let's just re-implement this simulator because it's just those basic components. Let's implement those on your graphics card. So we used OpenCL. It's just a bunch of matrix algebra. This is what OpenCL and these other languages are meant for. Implement that, and we got something in the order of 500 times improvement. So that's huge. Okay, so it is now the case that if you want to run the current version of Spawn, which has gone up from 2.5 million neurons up to 6 million neurons, but the running time has gone down because we've switched from CPUs to GPUs, and since GPUs have gotten a lot better since 2012. What used to be 2.5 hours to generate 1 second of simulation, we're now down to about 10 to 20 seconds to generate 1 second of simulation. And that's for 6 million neurons. So that feels like a big improvement. That's 500 times improvement. We're still 1,000,000 times slower than the brain if we want to start doing things the scale of the human brain. So yay. Step in the right direction. That's helpful, but what else can we do? Well, fine. If you want to, right now, if you want to run something on a single GPU that's the size of the human brain, yes, it would be 1,000,000 times slower than real time. But this is a fairly parallelizable problem, right? There's you just run different neurons on different GPUs, have them all talk to each other. For people who have worked in parallel, large parallel systems before, they'll start being really worried in this case because in a lot of these times, the large parallel systems, the slowdown is the communication between the components. There's this cool advantage that weight matrix factorization trick means that if you have, say, 100 neurons on one GPU and 100 neurons on another GPU, and the first ones have to talk to the second ones, you don't actually have to send all the data from all 100 neurons from one GPU to the other GPU. What you can do instead is, since you've got that weight matrix, you can factor that weight matrix into the decoder and the encoder. You can put the decoder on one of those GPUs, do that part of the weight matrix, and then you end up with, say, only 2 values. Send those 2 values over to the other GPU, and then do the second part of the weight matrix. So that greatly drops the bandwidth problem. So that's wonderful. And so if we're like incredibly optimistic and feel like, okay, maybe that will magically give us a linear speed up. So if I double the number of GPUs, I run twice as fast. Even in that incredibly optimistic scenario, all I would have to do is say, buy 10 million GPUs, and just run it on that. That ends up being something in the order of 40 exaflops of computation. Should be totally possible, no problem. Yeah, maybe. That's okay. Well, I could buy all of those, but even just buying all of those GPUs and running that whole thing, that's 3 gigawatts of power. That's like a couple nuclear power plants. That's a problem. That's just not, and yeah, it'll get some better over time. So there is an exaflop computing system that is coming online nowish. There's a few other ones that are planned. They're all sitting around this range of 1 to 2 exaflops is 30 to 40 megawatts. That doesn't actually give, that's not a huge improvement over what I was just saying, right? We're still talking about a gigawatt at least of power. And people really aren't predicting that that's going to come down much, which is a little bit weird. And the reason for that, well, I mean, there's lots of predictions. So basically, I'm starting to get into the point right now where I'm starting to argue about Moore's law. Will computers continue to just wait a year and then everything's more efficient and faster? And there's some people who will argue that is still happening. I'm slowly being convinced by the data that says, that at least in terms of energy efficiency, things are definitely slowing down. That we're not getting any sort of we're not getting any sort of doubling of energy efficiency going on. Here's sort of a zoom in of that graph, and sort of the argument is that, look, even as we're getting chips, these microprocessors more and more efficient, there's just going to be some limit past which we're not going to be able to keep expecting computers to get more efficient and faster. Slightly controversial. Some people just want to believe that it'll just continue to get better forever. But there's certainly going to be, at anyway, some sort of limits happening. And I think we're in this odd situation where, look, the power that we're needing to simulate the brain, even at this pretty weird abstract level, like when I'm saying, you would need 2 gigawatts of power to simulate the human brain, that's itself really controversial, because that's meaning, look, for each neuron I'm doing like one differential equation. So that's a pretty abstract model of a neuron. And that's assuming that the only thing that's important in the brains is neurons and synapses. So that's highly controversial and highly optimistic. And even in that situation, we're still this, saying, okay, it's going to take, with modern technology, 2 gigawatts of power to simulate the brain. The power consumed by the actual brain is more like 20 watts. Why is there this huge difference? Why are brains so incredibly much more efficient than all this fancy computer hardware we're using to simulate the brain? Especially when there's tons and tons of industry effort to make these computers as efficient as possible. What's going on here? So what some people have decided to do is, look, maybe a big part of it is these computers that we're generating, these computers that we're running all of our simulations on. I mean, GPUs were designed for doing graphics cards. That's what the G means. It's graphics processing unit. And there's tons of things in normal CPUs that are not needed when we're running these brain simulations. So let's make a computer, totally normal standard digital computer, but let's strip out everything that we're not using when we would want to do this neuron simulation stuff. So this particular project that we're seeing here is called Spinnaker out of the University of Manchester. And basically what they've done is they take the processor that you would find in your cell phone, these ARM cores, and they just take 18 of those and shove them onto one chip. So those little square chips that you're seeing on the bottom right. And then you take these chips and then you cover boards with them. So this particular board here has 48 of those chips. Each of those chips has, so there's 48 on the board, 18 cores per chip. So that means you can start getting some pretty nice scaling. And so that's been part of the Human Brain Project. They've got that working. It's up and running in Manchester. It's scaled up pretty big now. It's scaled up to the size where, in theory, you should be able to run models the size of 1/10 of the human brain. And it's there, and it's available. Now, it's still running about 30. If you wanted to scale that up to the full human brain, that would be sitting somewhere around 30 megawatts. There's another project going on to develop Spinnaker 2, which is just, all right, let's do the same thing, but with modern technology, because it's been 10 years since these chips came out, so let's make new ones. And that should reduce that down to, we're hoping, or somewhere around 3 megawatts if someone wanted to scale that up to the human brain. That's great. Huge improvement. We've interacted with them a fair bit and made sure that Nengo, so the same models that you were building so far, you can just run them on these, because you shouldn't have to change your code in any way in order to go run on this sort of hardware. So that's one of the nice advantages of Nengo, is we should be able to retarget these things, or take your model and put it on different platforms. even though the particular neuron model that's being implemented on that chip is maybe slightly different. Cool. So that's one thing that's out there. Can we do better than that? That's still, 30 megawatts right now, 3 megawatts in the future, assuming everything goes well. Those are still big numbers. And one interesting and somewhat controversial idea is, hey, look, this whole digital computer thing, this whole ones and zeros, maybe we don't want a computer that works with ones and zeros. Maybe we want to go back to the old days of analog computing. So forget turning everything into ones and zeros. And one of the arguments there is, look, this whole idea that computers are all just ones and zeros, ones and zeros don't exist. All there is voltages. And there's just a lot of mechanisms in computing that make sure that, things that are near a voltage that's near what they define as zero ends up staying at zero, and things that are near one end up staying at one. And it turns out that something in the order of like 90-95% of the power consumption is about keeping the zeros at zero and the ones at one. And it's keeping these nice clean signals such that the rest of the computation can actually work. It's because we've gone ahead and designed everything to be digital. So let's go ahead and try doing this a little bit more efficiently. Let's go to this analog computation. Let's take those differential equations that we want to have as our neuron model and literally just implement those in transistors and resistors and capacitors. Put those on the chip, and then poof, you get incredibly efficient. Let's actually have the physics itself do the simulation of the neuron dynamics. Like that would be incredibly efficient. So here, for instance, is a transistor level circuit that is an exponential integrate and fire neuron. I can't read that, but I will trust the I will trust the publication saying yes, okay, that works, great. But yeah, you can take differential equations and implement them in transistor logic. There's been, however, there's a reason that people tend not to do analog computation. And one big issue that sort of traditionally comes up is, hey, look, even if you go write out that circuit and then you go and manufacture that chip with, say, thousands of that circuit on it, the manufacturing process isn't perfect. I mean, these transistors that we're talking about, we're starting to talk about, you start counting the number of atoms involved in these transistors, and they're not perfectly aligned. There is variation in the manufacturing process. There are what they call transistor mismatch. So when you manufacture a chip, you say, okay, I want this transistor to have this particular property, resistance, capacitance, things like that. And on average, you end up with that, but then the manufacturing plant says, gives you a data sheet beforehand that says, okay, look, this is what sort of distribution you should expect to have around whatever it is you've asked for. All right, and this is why chip manufacturing gets so complicated, and why it is that some chips will run faster than others. And so that's sort of been a problem for analog computation. It's like, go ahead and look, this is the neuron model that I want, and I'm going to get, every single neuron on every single chip is going to be slightly different. So this is the transistor mismatch problem. It becomes worse and worse and worse the smaller scale you go. Yeah, each neuron on each chip has different properties. So traditionally, that's a big problem. We run into that and we're like, hold on a second. That's a good thing. I want all of my neurons to have different properties, right? Like when we were generating these sorts of pools of neurons, and I was showing, here's the response of lots of different neurons. We made sure that each one has a different firing rate and a different tuning curve. So this is actually perfect. This is what we want. The main thing that we would have to do is just make sure that we get the right sort of variability. So we make sure that the distribution that the manufacturing process gives you a nice variety of tuning curves. Okay. Which is a little bit tricky. So I spent 5 years on a project with Kwabena and Rajit. They're on the right. They had previously built a chip called Neurogrid, which was one of these analog neuron chips. So just exactly what I just described. And with the approach that they were doing, they ended up having something like somewhere in the order of 1 million neurons running in 3 watts, which, if you scale that up to the human brain, we're talking about maybe 300 kilowatts to do the full human brain. That's a huge improvement over even what the Spinnaker folks are hoping for. Now the problem with Neurogrid was when they designed that, they didn't make it particularly programmable how to connect the neurons. All right, so they didn't let you do something like, for instance, what you would want with the NEF of saying, okay, look, here's the connection weight that I want between these groups of neurons. So we did I spent 5 years on a project with them making the next version of that, which we called Braindrop. And the idea there was to actually design something like the NEF right into the chip itself, and do as much as possible in the analog domain. So for instance, the entire encoder got done in the analog domain. And just very weird. So basically what we did is we ended up saying that the encoder ends up happening in the analog domain. So that gives you your distribution of tuning curves. The decoder ends up happening in the digital domain. And with that sort of trade-off, we got some pretty good results. So that ended up being another order of magnitude faster and more efficient. However, we only ever managed to make a small version of that chip that only had 4,000 neurons on it, and so we're still hoping to go farther with that. There's other sorts of custom hardware out there. I always have to mention also brain scales, which is sort of the other direction for analog computing. What they decided to do is they decided to just say, hey, look, the biggest thing with neurons is connections between neurons. And if you got all these separate chips, it's a real pain to actually run wires between the chips. So let's just make one giant chip the size of so that picture there in the top right, yeah, that's they just made one giant chip that size. And they decided, hey, a lot of the applications of neurons are things like learning, and that takes a while. So instead of designing the dynamics to be close to real time, so for instance, with the Braindrop chip that we made, there's if a spike happens, and then the effect on the next, and then the effect that spike has on the next neuron, it suddenly has a large effect, and then it slowly decays back down. The thing that in biology would be the release of neurotransmitter and then decay back down. There's a time scale of that delay, right? And in biology, it's somewhere between 2 milliseconds and 200 milliseconds. And so that's what Braindrop targeted to make sure it would have the same time scale. In brain scales, what they decided to do is say, hey, look, let's just do all of that stuff, but make it 10,000 times faster than real time. The drawback of that is, of course, it's going to be 10,000 times more power consumption. So they ended up, so it means that you're just, burning a lot of power in order to run it that fast. That's fine. But that does mean that that they can sort of explore these learning models very quickly. For sort of comparison, if you really want, you can run those 200,000 neurons in something like 4 kilowatts if it was all slowed down to real time. So that's at all. We're still not at the point of anywhere close to what biological brains can do. Sorry, so let me take a step back here. That was a weird we're just sort of whirlwind across what is going on right now in terms of weird hardware for simulating neurons. Terminology-wise, it's sometimes called neuromorphic hardware. So it's hardware that is designed to simulate neurons. There's a bunch of these things out there. And I feel one thing that sort of excites me about that whole process, about the fact that those things are out there, is that I feel that it's at least possible, that human scale simulations could be done in my lifetime. If it wasn't for this weird hardware, if I had to just rely on GPUs, I'd be much more sympathetic to the argument that, okay, look, all this neural modeling stuff is cool and all, but you're never going to be able, it's just not going to be practical, because you're never going to be able to run the models the size that you want, or at least not within the next 100 years. So, and I think if I was limited to GPUs, I'd start to have real worries. But the fact that there is this other sorts of hardware coming along means that, yeah, okay, it's at least possible that I could run human scale simulations. Of course, I do always have to put the caveat in when I say, okay, yes, it would be possible to run human scale simulations. If someone gave me that computer right now, I have no idea what algorithms I would even try running on it yet. Right? We don't have yet good theories about what all those components would be. It would be great to, even try to start exploring those things. And you'd need that sort of hardware in order to start exploring those things. So just having the hardware wouldn't solve the cognitive science problem. But it would, it would at least be helpful. That said, for research right now, I highly recommend, if you're doing research right now that's using this sort of neural details, look, GPUs are what's available right now. Okay, they're cheap, they're available, and they'll scale up pretty far. I would start worrying past, say, 20 million neurons, but there's still a lot that we can do with 20 million neurons. And so for the next maybe 5-year time frame, I'm sort of happy limiting myself in that range, while still keeping an eye on all this neuromorphic hardware and where is it going. And because there's a lot of interesting possibilities. There's this custom neuromorphic hardware, FPGAs are becoming more possible in that direction. All of that stuff is great. And one of the things we're really trying to make sure happens with Nengo is, look, anything that you develop that runs on your normal Nengo, you should be able to just push a button and run it on whatever other weird hardware that Nengo supports. All right, so that's the goal. It works in some cases, but that's what we're looking for. Okay, cool. I think one really important other aspect in there is that the chips that I've talked about so far are all research chips. So this brain scales, this brain drop, and Spinnaker, wherever that is. Where's the slide? There we are, Spinnaker. So all of those chips are all meant for research. And there's definitely also this worry that, well, until industry really grabs attention of this, or really comes in this, it's going to be hard to know whether or not this stuff is going to be feasible. So it's also worthwhile to take a quick look at some of the industry players in this realm. So one of them is TrueNorth. That was sort of the first big one where they sort of really hit this target of let's put 1 million neurons on one chip. That's great. They managed to do that is an incredible technical feat. And running that because if you've crammed that many neurons down on one chip, you also have to run it efficiently, otherwise the chip will melt because it's all just so small. And they got that to work great. However, in order to fit it all onto that one chip, they ended up making it such that there's a very simple neuron model and very simple synapses. Basically, you end up with binary synapses. So the synapses are either there or they're not. And then you can do some fun trickery in order to sort of, group a few neurons together or group a few synapses together in order to get, you can maybe get like 4-bit weights or 6-bit weights and things like that. But then when you do that, you then start having fewer than 1 million neurons on a chip. So that was sort of, I think, one of the first big industry players in this space. And it ended up being just sort of difficult for people to use. I'd say that the next big industry player that got in here, though, would be Intel's Loihi chip. They went with a slightly smaller chip. They decided, okay, we're going to aim, it's 128,000 neurons on a chip, but make it highly programmable. And their argument was there, well, look, we have no idea what the right algorithms are going to be and what the right components are going to be. So let's go ahead and make it flexible while still being pretty compact. And so it's got a bunch of different, it's a configurable neuron that you can do leak, integrate, and fire. You can do multi-compartment neurons. You've got exponential low-pass filters for your synapses. And they also did something that TrueNorth did not do, and is that they also had built-in learning rules. So this is the chip over here. It's sort of a, this is zoomed in, so the actual chip itself is, I don't know what it is. It's going to be a couple centimeters across, something like that. So these are all the different groups of neurons across here. And then they also included on the chip, because it's Intel, they just crammed in 3 Pentium class CPUs on there as well. So you've also got standard, some standard programming capability in the chip. So that makes this a very flexible thing. Intel, when they put this chip together, they decided they needed some sort of demos on it in order to see what it might be good for. And they actually hired the lab that I'm a part of, or that I was a part of at Waterloo, has a spin-off company called Applied Brain Research that I was also a co-founder on. Am also a co-founder on. Anyway, so they hired Applied Brain Research to make some demos to show off what this chip can do. And so we did things like keyword detection. All right, can we? And that we'll be showing better data in a moment. But the idea there is with a lot of voice recognition systems, voice recognition takes a lot of power, and so you tend to want to have just sort of a couple of keywords that it's sort of initially looking for to know whether or not you should wake the whole system up and do the full voice recognition. So that's why things like saying "Okay, Google" lets you start a voice recognition system, and basically what you then need is you need a really, really energy efficient system that just looks for those keywords. And so there's some fairly standard neural networks out there that can do that keyword detection. We implemented those, showed that Nengo can also implement those, and can run them on their hardware.
Controller, so we'll turn it on.
We also, we also implemented some simple motor control problems, because motor control is something that you can do nicely with neurons. This video that I just showed there, that one's not running in Loihi, but I'll show you one in a moment that is. But the idea here is, hey, look, let's just take motor control algorithms, implement them using Nengo, and then use Nengo to put them on chips. All right. And of course, that video is not going to work. I am going to show that video in a second. There we go. There's the video. So what we did is take a very simple motor control algorithm, and we wanted a motor control algorithm that sort of takes advantage of this fact that we can do online learning. And so this particular task that we're doing here is just, let's learn the function that is how much extra force should the robot arm be applying right now. And so the idea is, so if you have, say, a heavy weight on an arm, it might not work very well. All right, so let me take a step back and describe what's going on here. Standard robot control. We have something. It's called non-compliant. Is the standard robot control. This is why robots are dangerous. You tell the robot arm to go to a position, and it goes there. And if your arm gets in the way, then it breaks your arm. Right? That's standard. How? Yeah, that's why you put danger tape around things. The alternative is compliant control. One alternative, and that is, hey, you've got a good physics model of the environment. Just figure out how much force you should be applying, and apply that much force. And that means that's nice and safe, because that means people can shove the things around and there's no extra forces involved. But the problem is, if you give an extra unexpected weight to the system, then it's not able to compensate for that, because it's like, oh, I'm just calculating how much weight I should be applied. Someone's given me an extra weight on. I can't learn. My physics model of the world doesn't let me know what's going on here. So what you want is a neural network that'll go ahead and learn to compensate for that. So there, we've put it on this adaptive controller, and now you can see the neural network that is just learning the function, hey, given where my arm is right now, how much extra force should I be applying? Okay. And that's just a function, in the same sort of way of all the functions that we've been showing so far. And so a simple learning algorithm will let you do that. We'll talk about the learning algorithm a little bit more in one of the later lectures. Right, and so anyway, we were able to take that algorithm and go ahead and implement on this chip, and then let it go ahead and, takes a few seconds, but after a few seconds it will go ahead and adapt to do that. That algorithm ends up coming out of a model of the motor cortex in mammals. All right, so that was basically what we were really attempting to do, was try to show that there's sort of industry reasons to have these sorts of chips. Because I think it's really great that industry is interested. But in order for it to scale up, in order for these chips to be as available as, say, GPUs are now, there needs to be some sort of really compelling reason for industry to really get heavily involved. So one surprising possibility might be motor control, because you do need, a small neural network. You need a neural network that can learn to do this. Here what we're doing is having, showing that adaptive control works fine when it's trying to go to particular targets. Anyway, right, so we have all of this interesting hardware, interesting evidence of, hey, maybe this will be useful. The strongest piece of evidence I think that we have right now is that keyword spotting demo, where it is just this really simple small neural network. On the left is the power consumption for GPUs, CPUs, a couple of the different highly efficient GPUs and TPUs that are starting to be available, and then the energy consumption for Loihi. One sort of interesting, surprising thing here is just how much less energy efficient the GPU is than the CPU. And that's a function that GPUs turn out to not really be perfect for doing single neural networks. In a lot of, if you want to run a GPU efficiently with a neural network, you want to do what's on the right there, and that's this batch size parameter that's across the bottom there. If you're able to feed in, say, 64 inputs at the same time, so if I've got 64 different microphones out there, each all listening for the phrase, in this particular case, the phrase was aloha, because Loihi is a Hawaiian word. If you've got 64 different microphones out there, and all of them are all that information being fed to one GPU, then in that case, yes, the GPU ends up being very, very close to the Loihi, power consumption. But that's not what the actual case is. So basically what that's saying is GPUs are really good at matrix-matrix multiplies. That's what they're turn out to be really, really efficient at. But if you've just got one input coming in at a time, which is what happens with, with actual real use cases of neural networks, I just have one input coming in at a time. I mean, it might be a multi-dimensional input, but it's just, here is my input. It's not 64 different independent inputs. Then the GPUs end up being much, much less efficient than what we're looking for. And so we're really hoping that these sorts of energy efficiency measures are something that catches on in industry and lets us make sure that this sort of hardware is going to be available. I don't really care whether or not it's useful in industry. I just want industry to make this hardware for me so that I can then use it to run much larger brain simulations. So I'm really hopeful that that sort of thing is going to happen. But at the moment, GPUs are the way to go, and you can go pretty far with those. That's, I think, what I just said. Yep. Okay, so and I think there's all sorts of interesting industry applications now that you start getting into this lower power, 100 times less power consumption than normal GPUs. That's pretty accessible right now. Much lower latency because you have you don't have to do a lot of neural network type things right now are done by, say, you record the data on your cell phone, and then the cell phone just sends that off to a cloud somewhere. It does the computation and sends the result back. So there's all sorts of latency problems there and privacy problems. And in theory, we can use this sort of approach for any sort of algorithm that's well suited to implementation by NEF. So anything with vectors, smooth functions, and smooth differential equations. As sort of a side note in there, there's a huge discussion that goes on when people are making these hardware neuromorphic computing things, which is why have spiking neurons? And this is a fascinating and long and huge debate. I will toss in my little bit of, here's my point of view on it right now. It is definitely something that could be a full discussion on its own. But this question of why have spiking neurons has been around for a very long time. By spiking neuron, I mean a neuron whose output at any given time is either a 0 or 1. And there's a couple different, so why would I argue for this spike? Because a lot of the examples I'm doing are spiking. If I'm talking to an industry audience about why spiking, part of it is, or like one answer is that, look, there's interesting dynamics that can end up happening there. So often spiking neuron models have some sort of internal dynamics within the neuron itself. And that does mean that you get to approximate slightly different classes of functions. Okay? And that's just exactly what I've been saying in the NEF, is as you change your neuron model, that's going to change your tuning curves, and that's going to change what class of functions you can well approximate. It's a little tricky in that it's really hard to pin down exactly. I mean, that's sort of one of our ongoing research topics, is trying to pin down exactly what sort of dynamics is good for what sorts of classes of functions. But even though that's sort of like the common answer about why spiking, technically that doesn't have anything to do with spiking. Technically, whether or not a neuron has internal dynamics, I could have a neuron with internal dynamics and its output is non-spiking. Right? I could do that. It's incredibly rare. It tends to just be that that when you go to a spiking neuron, people do tend to make it have internal dynamics. I mean, technically, this question of why have spiking neurons, if I was going to compare a neuron that can output any value at any point in time versus a neuron that can only output zeros and ones, if that's my only point of comparison, then by definition the spiking neuron has to be, less capable than the full thing, because outputting a 0, 1 is a subset of outputting all the numbers. So I tend not to focus on the computation side, like, oh, hey, by doing a spiking neuron, there's new computations that I can do. I would love to be able to find examples, and I think it's possible for us to find that there will be some examples. It won't be about whether or not it's spiking. It'll be about whether or not the neuron has internal dynamics. But that will be a direction of research. But right now, when talking to industry, if I wanted to say about why spiking neurons, it's all about energy efficiency. And this energy efficiency argument is, well, hey, look, if I have a spiking neuron whose output is 0 or 1, and I need to take that output and multiply it by a connection weight, well, if I know my outputs are 0 and 1, then I've just converted multiplication into addition. Right? That is, okay, that's going to help. And then what the trade-off is, so if you've turned your multiplications into addition, your trade-off is now this is kind of a noisy addition. And we can compensate for that by doing the low-pass filter. That's the synapse, when the neurotransmitter is released and then it's gradually reabsorbed. One way to think about what's happening there is, hey, look, the spike happened at this point in time, but it's also telling you about things it's also having its effect over a small window in time in the future. And you can think of that as kind of like a smoothing operation on this noisy multiplication that is happening because of this spike. Okay? And that's fine as long as your values are changing smoothly over time, which for biology is definitely the case. So, if my input is, say, what my eyes are seeing, or what I'm hearing, all of those are situations where you can actually say how quickly do those sorts of things change over time. They're pretty smooth, and the contrast there is, say, something like if I have an image recognition system that I'm just shoving like random images at, and every time step I just give it another image, a totally separate image. That'd be a situation where this sort of smoothing over time is a bad idea. So I do think there's going to be some situations where we can talk about spiking being useful, and some situations where non-spiking is useful. Certainly in situations where my input values are changing smoothly over time, that's, I think, exactly a situation where you can get this huge energy efficiency win by switching to spiking neurons. That said, of course, this energy efficiency win only exists if you have hardware that directly supports spiking neurons. For most researchers, that'll be sort of an abstract point, but that's going to be, I think, the sort of argument that we'll need in order to convince industry to start making these sorts of energy efficient chips that would let us scale these brain models up really big. Okay, that was a big, long whirlwind of hardware, but I think it's important to keep in mind in order to know that, yes, the sorts of systems that we're talking about in this course, in the long run, we will be able, hopefully, to scale these things up very large and start being able to talk about large brains. Right now, we're a little bit limited, but I think there is promise in the future. Okay, I'm going to cut this here and then do a second part of this talk that'll start getting more into the scaling up to symbolic reasoning. Thank you.